Finally, systems can also reach what are called physical equilibrium. We'll focus on two major types of physical equilibrium, phase equilibrium and solubility equilibrium. To look at a phase equilibrium, if we imagine we have a stoppered flask with some water in the bottom of it, what would really be going on in this flask from time to time is one of these molecules would become a liquid, or a gas, I'm sorry, and another one of the gaseous ones might become a liquid. So we might have this guy pop down here, well, this guy pops up here. Overall, what's occurring, because the rate of evaporation in the flask is equal to the rate of condensation, we have an equilibrium. Because of equilibrium, rates of two opposing processes are equal. So what's going to happen as long as this flask is stoppered is the concentration of liquid and the concentration of gas are going to be the same. Currently have 9 in the liquid stage and 4 in the gaseous stage. As the system continues to change, they're really just going to be flip-flopping, and there's going to be no change in the overall amount of liquid or gaseous particles, since the rate of evaporation is equal to the rate of condensation. However, if we unstopper this flask, we have now shifted this equilibrium, because these particles can now leave. And it also allows these guys to be able to easily become a gas and lowers their chance of being turned back into a liquid. So a lot of these particles are going to be able to leave. We're going to definitely have a change in concentration of liquid and gas particles in that container. So water in a sealed flask, we have an equal concentration. Oh, I did not mean that. Sorry. We have an equal rate of condensation to a rate of evaporation. The concentration of liquid water and water vapor, remember, are staying constant. Both of those. If we open that flask, we are no longer at equilibrium. We now have one rate greater than the other one. The rate of evaporation is greater than the rate of condensation. Over time, what's going to happen is we're going to have a decrease in our concentration of liquid water. So since we have an increase in the rate of evaporation, we have more and more water vapor. That water vapor is leaving and not condensing again back down into a liquid. So we have an overall decrease in our amount of liquid water. So because our concentrations have changed, we are not at equilibrium anymore. We could also shift this. Again, this is a phase equilibrium. And this could be shifted also by changing temperature. So opening or closing the flask is one way to change this. Another way would be if we increase temperature. If we were to increase temperature, we would have an increased rate of condensation. I'm sorry, not of condensation. Sorry. We would have an increased rate of vaporization. And therefore an increase in our water vapor. Whereas if we decrease the temperature in this flask, as these guys lost their kinetic energy, they might be more likely to turn back into a liquid phase. So now our rates would not be equal anymore. We'd have an increased rate of condensation. In this case, we would have an increase in the concentration of liquid water. Saturated solutions are also another form of physical equilibrium. If we actually put some salt into water and allow it to dissolve, the water molecules are actually picking up salt ions and carrying them away in the process we call dissociation. Now, when we talk about a saturated solution, which takes you back to table G, there's a certain amount of solute that a particular solvent can hold at a particular temperature. If we have a perfectly balanced out saturated solution, the rate at which these little water molecules are trying to take ions up out of the solution is the same as the rate at which some of the ions are trying to go back into the crystal. So we have two opposing processes here. We have dissociation and we have crystallization. When a solution is saturated, these two rates are equal. Therefore, the amount of dissolved salt remains the same. Solubility equilibrium or physical equilibrium can be shifted by something called a common ion. If we imagine we have a solubility equilibrium, such as a saturated solution of NaCl. This NaCl, remember, is trying to dissociate into NAs and Cls that float around in solution. Well, those individual ions are attracted to each other and try to turn back into that solid NaCl crystal at the bottom. If we were to add some silver chloride solution to this, what would actually happen, since we're adding a Cl to a solution that already has a Cl in it, we're actually adding something called a common ion. So what we're doing here is we're actually increasing the amount of Cl in our original solubility equilibrium, which will shift this equilibrium to the left. What that's actually going to cause is an increase in the amount of NaCl solid forming in solution. Really what happens here, because we have more Cl's, there's a higher probability that they'll collide with Na and form solid sodium chloride in the crystal at the bottom of our container. The amount of Na ions is actually going to decrease as they get reacted to the Cl. This is very much like the shifts in equilibrium that we talked about earlier in the unit. We added Cl. When you add, you shift away.